Let's travel back in time to the early 2000s, when America was on the cusp of a nationwide poker boom. Available on VHS rental is Matt Damon and Edward Norton's high-stakes poker drama, Rounders. The World Poker Tour is about to debut on Travel Channel, and Chris Moneymaker will soon win over $2 million in the World Series of Poker main event. If you want to play poker online, you can do that too, at sites like Planet Poker, the world's first real money card room for playing online poker. But Planet Poker has a problem. Well, two problems if you count the fact that the US government's about to pass a law making online gambling illegal. What concerns us is Planet Poker has a marketing problem. Back 20 years ago, many people felt uncomfortable spending money on virtual cards and gambling. I know, from the perspective of the modern innovations in loot boxes and mobile gaming monetization, it's hard to believe people were reluctant to spend money online, but 20 years ago was a different time. So how did Planet Poker try to get people's trust and attention? Well, they advertised 24/7 action. They called themselves the most trusted card room on the internet. And they emphasized that despite being virtual and online, you were still playing real poker with real people. They did one other thing too that was pretty interesting. For a brief period, if you went to the Planet Poker FAQs, they showed you their actual code to shuffle decks, so everyone could see what is happening with full transparency. Here it is. Here's their code. We can see exactly what they do and build our confidence about virtual poker. Unfortunately, we'll see there's more than one issue in this code. In fact, shortly after they posted it, the code was quietly taken down. But not before security researchers were able to craft and execute an impressive exploit that jeopardized every real money game played on the site. So let's dive into some algorithm analysis and try to crack online poker. The first thing to notice is that this code is written for the Delphi 4 Pascal IDE. I imagine most of my viewers are unfamiliar with the Pascal programming language, so let's update the code to a more modern Python implementation. I've done my best to keep all of the original logic intact, including the key issues. So here we have a deck class with an initializer that creates the numbers 1 through 52. These represent the 52 cards you might see in a deck. We then have our shuffle function, which randomizes the order of the cards. Here's the critical part of the shuffle. It takes two cards and swaps their places. Let's just look at the shuffle algorithm being used here, cleaned up slightly to be even easier to read. You can see we loop through each spot in the deck I, then pick a random spot J, and swap the two cards at positions I and J. We do this for each of the 52 spots in the deck, and that will be our complete shuffle. Let's bring back the original Pascal code so we can see our first issue. When we loop over each spot, we consider all 52 different cards in the deck. But when we pick a random spot, we only look at 51 different spots, so not every card gets shuffled equally. Oops. Well, it's very easy to make these kinds of off-by-one errors. Not a big deal, but it's never fun to have these kinds of errors in public-facing code that was supposed to make people feel more comfortable with your service, especially when the code is determining who wins hundreds of thousands of dollars each day. So this is an easy fix in Python. We can get rid of the needless subtraction and get the code we intended to write, but we still have a bigger issue, and this time it's a lot more subtle. To understand what happens, let's simulate this virtual shuffle with a deck of just 3 cards, ace, king, and queen. First, I is set to 0, so we look at the starting card, the ace. Next, we pick a random spot. Oh, it seems like the queen was picked, so we'll swap the ace and the queen. This was our first time through the loop, so we need to do this 2 more times, once for each other spot in the deck. We're now on the second spot, which holds a king, and our random number has picked, the first spot with the queen. So we swap these 2 spots, and this is our second time through the loop. And now our final time through the loop, our random number picks, the third spot, the ace itself. Well, you can't really swap a card with itself, so we'll just leave the ace where it is. And that's it. We finished the loop and shuffled the cards. The ace, king, and queen have been reordered as king, queen, ace. Seems shuffled to me. What's the problem? Let's run through the process again, but this time we'll look at a tree of every possible outcome simultaneously. Starting with ace, king, queen, step 1 is to swap the ace with one of 3 possible places. That means the ace can either stay where it is, swap with the king in the middle, or swap with the queen at the end. That means after the first time through the loop, we have these 3 possible outcomes. Now for the second time through the loop, we'll look through the possible swaps for each of the cards in the second spot. First, let's assume ace, king, queen. Second time through the loop means we're looking through the second card, the king in this case, which can swap with the ace. It can stay where it's at, or it can swap with the queen. Likewise, if the first loop left us in the state king, ace, queen, the second card is the ace, which can swap with the king, stay where it's at, or swap with the queen. Likewise, if the first loop left us in the state queen, king, ace, the middle card, the king, can either swap with the queen, stay where it's at, or swap with the ace. That's it. That's all our possibilities for the second time through the loop. We have one more time through where we're going to take the third card and swap it. For the third and final time through our loop, our deck can be in one of these 9 states. And each of these 9 states has 3 possible swaps for the third card. It can either swap with the first card, the second card, or stay where it's at. So in total, that's 3 choices for the first swap. And from each of those choices, there's 3 new choices for the second swap. And from each of those choices, 3 new choices for the third swap, for a total of 3 to the third, or 3 times 3 times 3, which is 27. 27 equally possible paths through our shuffle code, which means there's 27 equally likely shuffle results. It should be pretty clear these results are not all unique. For example, sometimes we swap a card, then swapped it back. To count unique rearrangements, we can see we have 3 spots we can put the ace. Once we've made that choice, there's 2 places left for the king, and then 1 spot left for the queen. So that's 3 times 2 times 1, or 3 factorial, which is 6. There's 6 possible unique arrangements. Ace, king, queen, ace, queen, king, ace, queen, queen, ace, king, and queen, king, ace. I think you're probably starting to see the problem now. We have 6 possible unique arrangements of our cards, but our shuffle leads to 27 equally likely outcomes. The issue is you can't split 27 things into 6 even buckets. If you look at the output of our shuffles, you can see that some results, like ace, queen, king, happen more than others. We have a biased shuffle. This method will never work, as the n-to-the-n paths through our shuffling code will never be evenly divided through the n factorial different shuffles for any value of n3 or greater. So what's there to do? How can we fix our shuffling? The solution is actually extremely simple. First, here's the biased shuffle code we just looked at. And now here's the fixed code. Notice the difference? Look here. That was a 0 before, and now it's an I. This means we don't swap the card at position I with any random spot, but we only swap it with places further down the deck. This means we can never undo a swap with a future swap. Once a card has been placed at position I or earlier, it's now there for good. Let's run through all the shuffle possibilities again to see why this works so well. Again, we'll start with ace, king, queen. And again, the first loop through the shuffle, we'll look at the first card, the ace, and we can swap it with any of the other 3 positions. The ace can stay where it is, swap with the king, or swap with the queen. The second time through the loop, something has changed. When we consider the second card, here a king, we can no longer go backwards and swap with the ace. This is not allowed. In this case, there are 2 legal swaps, either keeping the king where it is in position 2, or swapping it with the queen in position 3. If we had the case where the ace was the second card instead, we have the same logic. We can either keep the ace where it is in the second spot, or swap it with the third spot. Likewise, if we had king, queen, ace with the king in the second spot, then we can either keep the king where it is in the second spot, or we can swap it with the ace in the third spot. On the third time through the loop, we have no choices. The third card can't swap backwards as it's the end of the list, so it has to stay where it is. Looking back, we've had 3 choices for the first swap, 2 for the second, and 1 for the third. That means we've had 3 factorial, 3 times 2 times 1, or 6 different equally likely paths through our shuffling algorithm, and each path ends in exactly one of the 6 possible outcomes. Let's put the 2 shuffles side by side. For a deck with n cards, the broken biased shuffle had n loops, each with n random choices to make. That means n times n times n, or n to the nth power, different paths through that shuffle code. N to the n different possible shuffles. For a fixed loop, we have n choices the first time, n minus 1 the second time through the loop, n minus 2 the third time through the loop, and so on. That's n factorial different choices, which matches exactly the n factorial different possible shuffles a deck can have in theory. So we fixed our off by 1 error and have a fair and unbiased shuffle algorithm. We should be good to go with our shuffle code, right? What could go wrong? Well, from just outside of Washington, D.C., in a city called Dulles, Virginia, a press release has been released from a security group at the company RST. Let's check it out. The software security group at Reliable Software Technologies has discovered a serious flaw in the implementation of Texas Hold'em poker. We have exploited this flaw in the lab. Our exploit allows a player, us, to calculate the exact deck being used for each hand in real time. This means a player using our exploit knows the cards in every opponent's hand, demonstrating, without actually cheating, that it could be used against real money casinos. Scary stuff. So, what exactly did this software security group find? Well, 1, there was the off by 1 error in shuffling. 2, a biased shuffle algorithm. 3, concerns over poor pseudo-random number generation. And 4, too few seeds being used to make these random numbers. We've already discussed the first 2 problems, so let's dive into the random numbers. Random numbers from a computer algorithm are not truly random, but rather based on mathematical procedures. For example, the linear congruential generator method likely used in Planet Poker looks like this. What happens here is that you take the previous random number, called a random seed, multiply the seed by a constant, add 1, then take the remainder after large division. The result of this process is the next random number, and it's also the new random seed for the next time a random number is needed. See my previous video for more details on random number generation. What you need to know here is that once you know a random seed, you can run this very deterministic algorithm again and again to predict every random number you'll get in the future. Just knowing a single random seed will tell you all future random numbers. But where does the first seed come from? Well, we can see in the original shuffle code that the random.seed function is called each time a new shuffle occurs. This function resets the random seed. How does the random seed get selected? Well, the details vary system by system, but the most common approach is to set the random seed to the current time as measured in milliseconds since midnight. Okay, time for a counting break. How many total shuffles exist in a 52 card deck? Well, 52 factorial. That it's 52 times 51 times 50 times 49, etc. This number is truly mind-boggling. 52 factorial is 81 unvigintillion, I think. It's a 67-digit number. For perspective, you could take every single atom on planet Earth and stack $1 trillion on each atom, and you wouldn't even be 1/10 of 1% of the way to 52 factorial dollars. So what about random seeds? How many different random seeds are possible? We can't actually have 52 factorial different random seeds because in the code I showed you, our random seeds are stored in a 64-bit number. That means there's only 2 to the 64 different possible random seeds in theory, so only 2 to the 64 shuffles possible in theory by our code. 2 to the 64 is not some 60-digit number monstrosity that you get out of 52 factorial. It's in fact a much more reasonable 18.4 quadrillion, or 18 billion billion. This is a slightly less mind-boggling total, but it's still huge. For example, it's still larger than all the grains of sand on the planet. In fact, 2 to the $64 is enough money to make everyone on Earth a multi-billionaire and still have $1 quintillion left over. So in theory, we have 52 factorial possible shuffles, but the random seeds are stored in a 64-bit number, so there are only 2 to the 64 different random seeds possible, meaning we can only ever see 2 to the 64 possible shuffles. This is probably not a big issue, as 2 to the 64 is still such a big number. What is a problem is when we think about how the random.seed function works. How many values can it have? Well, that's a question of how many different values are there in terms of milliseconds since midnight. There's only 86.4 million different milliseconds, and then we wrap back around to 0 once midnight hits. This is a much smaller number than 18 quadrillion. Only allowing for 80 million different shuffles is already bad, but the researchers at RST Software Security Group pointed out the problem is much worse, because the random numbers generated are tied directly to the system's time. If you can synchronize your clock to the clock of the computer server shuffling the cards, your random numbers would match exactly the random numbers on the server. In practice, if you know what time zone the server's in, you'll only be off by 1 or 2 minutes when you try to synchronize the clocks, meaning there's only about 200,000 or less different shuffles to check, different possible random seeds you can get. To a computer, checking 200,000 things is nothing. This laptop I'm recording on can process over 3 billion operations each second. Probably your smartphone can too. So here's how you crack online poker. Before you start, synchronize your computer to the time zone of the poker servers. Then, try a potential seed for the random number generator. Shuffle the cards using the seed, and deal out this shuffle to see if it matches a card you've seen so far. If there's not a match, go back to step 1 and try a new seed. If there is a match, you're done, and you know every single future card coming for the rest of the game until the next shuffle, at which point you just repeat the whole process. Maybe there's a small step I skipped. How do you know which cards to match your test shuffle against? Well, this involves knowing how Texas Hold'em works. Here's a screenshot the researchers shared from a Planet Poker game they were trying to crack. In Texas Hold'em, you have the flop. That is 3 communal cards which are immediately shown to everyone at the table. You also have a private hand of 2 cards, which you can combine with the communal cards to make a poker hand. This actually gives us 5 known cards at the start of the game, 3 from the flop and 2 from our private hand for a total of 5. Now we quickly try a few 100,000 shuffles from different seeds to see which one matches these 5 cards. And in less than a second, we'll know the exact shuffle. We can then simulate out the deals to everyone else at the table. And because we know the random seed, we know what cards our opponents will have. The researchers developed exploit software to demonstrate the entire process to show everything works smoothly in live games. Such a tool gives an intense advantage, and as the researchers point out, there was likely over $100,000 every day of real money poker games waiting for somebody to unfairly win using their knowledge of algorithms, randomness, and computer security. So, what should you do if you find yourself programming a high-stakes piece of software that depends on randomness? How can you do better? Well, first, use an unbiased shuffle. The approach we saw here is essentially the Fisher-Yates algorithm as popularized by Knuth. Second, we can use a high-quality pseudo-random number generator. We've seen LCGs here, but I'll show even better methods in a future video. And finally, and most importantly, use your full 64-bit random seeds. Testing 18 quadrillion different shuffles would take months or years on even the fastest computers, rendering this entire approach impractical as a way to gain an advantage in real online play. It's still important to make sure that this initial random seed is picked in as unpredictable a way as possible, such as by observing some of the physical randomness that's in the world around us. But that's a topic for a future video. Thanks for watching, and I'll see you next time.